In terms of torques, what is the criterion that something like a seesaw balances? So I'd like to start out by maybe revisiting what we already know about this situation in terms of center of mass. So if I've got two seesaws here, this one I'm going to look at for center of mass point of view, and then I'm going to go down and kind of redo things in terms of torque and see if we kind of get the same answer. So if these two kind of blobs here maybe represent two objects on the seesaw, maybe they're kids, right? But I didn't spend the time to put all the details for kids. But if one of them has a mass m1 and the other one has a mass m2, and let's say the m1 blob is a distance x1 from the fulcrum here, and the m2 blob is a distance x2 from the fulcrum there, and the fulcrum is at the center of mass point. But if I assume, I'm going to do this maybe a little differently than we did with an example in a past chapter. I'm going to assume that the origin is right there at the fulcrum, right? So I'm going to say that this is the origin for that system. So that really means that the center of mass is equal to 0. So I'm going to say 0 is equal to the center of mass position, which is equal to, normally we would write, I think, m1, x1. I want to think a little bit about minus signs in a second, though, right? Because there are potentially signs here with the origin that we've chosen. But this is the formula at face value that we usually use for center of mass. But in this case, since m1 is to the left of the origin, that kind of puts it in negative territory, I think. So maybe it would be appropriate to put a minus sign here. And since that's all equal to 0, I could just multiply both sides by the total mass to get a simpler looking expression of 0 is equal to minus m1 x1 plus m2 x2, which I don't know, there's different ways I could restate that. Like one simple thing is I could just say, well, let's add m1 x1 to both sides, right? And I get m1 x1 is equal to m2 x2. Sometimes I call this equation the simple seesaw equation. In other words, if you multiply the mass of the object times its distance from the fulcrum, that should be equal to the mass of the other object times its distance from the fulcrum. And if those conditions are met, the seesaw is going to balance. Now, how does that make sense maybe from a torque perspective? So let me look at that down here. So from a torque perspective, I'm going to say there's a force F1 that corresponds to the weight of mass M1. And then there's going to be a force F2 that corresponds to the weight of mass M2. And then if I look at torque for this, maybe I'd want to say that R1 represents the moment arm for the mass on the left, right? And maybe R2 represents the moment arm for the mass on the right. So that's kind of analogous to what I did with X1 and X2. I've just switched to using R's, which feels more torquey, right? And in that sense, maybe I could say, well, the torque due to the first one would just be equal to R1 F1. They are at right angles, so sine of 90 degrees is equal to 1, so maybe that's okay to just write that. And the torque for the second mass would be R2 F2. Something I might want to be a little bit careful about here, though, is that if you think about what direction do these torques want to rotate this system, the force F2, it looks like, is rotating the seesaw in a clockwise direction, whereas the force F1, I think, is rotating it in a counterclockwise direction. In other words, they have opposite senses of rotation. If I use the right-hand rule to do directions of these torques, let's see, for the first one, I would point my fingers to the left in the direction of R1 and then curl them down, and my thumb actually points in towards my chest right now, which is really out of the board. The other one, I'd point my fingers to the right for R2 and then down for F2, and it would point into the board as opposed to out of the board. So in that sense, what I just got there, right, was this one was out. I was just double checking, make sure I did that correctly because it's easy to screw up. Anyways, I'm just saying this one is out, this one is in. But another way I could maybe look at that is to say that maybe one of them is negative. Maybe I make this one a negative direction of rotation. So that would mean that counterclockwise represents a positive direction rotation. And that, if you think about like the way angles are defined in trigonometry, positive angle kind of is a counterclockwise direction of moving around the unit circle, right? And so maybe I've defined my minus signs in relation to that. But it turns out for solving problems with torques, the very formal vector definition corresponds to what these words describe. But if you just want to arbitrarily say, okay, this is going to be my positive direction of rotation, this is going to be my negative direction of rotation, and then you stay consistent with whatever you decided for that, that is always going to work. And you don't need to worry about complicated right hands and complicated vector mathematics. You just establish a direction of rotation to be negative and another one to be positive, and then look at the sense in which these things rotate the system, right? So clearly one of them must be in a negative direction, and I've defined this one to be that. So if I say, since it's asked me what is the criterion that something like a seesaw balances, and maybe getting a little bit ahead of our story because we're going to have a whole topic on that later on. But the basic idea is going to be similar to forces, where the sum of the forces would be equal to 0 means the forces balance. The sum of the torques being equal to 0 means that the torques balance. But in this case, so you could say, hey, there's two torques here, right? I've defined tau 1 and tau 2. But with the minus sign that I defined here, I would actually get R1 F1 minus R2 F2. So this is the condition I get from that, which is actually really the seesaw equation again. And you might say, wait a minute, it looks a little bit different than the one you said before was a seesaw equation. But the thing to notice is if I add R2 F2 to both sides, I would get R1 F1 is equal to R2 F2, but F1 and F2 really represented the weight forces. So this is R1 M1G is equal to R2 M2G. So I could cancel those G's if I wanted to, and then I'd wind up with the result R1 M1 equals R2 M2, which aligns with the result I got from thinking about center of mass. So kind of my intention with these examples, this is a preview of how torque really relates to rotation, and in particular why we can use it as a condition for whether an object balances or not. In the next chapter, we're going to look at objects that are not in balance and that the intention is to rotate them and see how torque does that. But let's check it with the answer here, and I think this aligns more with what I did in the second case. It says torques must balance. Moreover, the sum of the torques must be 0 in order for an object not to rotate. For a seesaw, this could be, and that was the equation I arrived at here. Everything I did after that kind of was to align it with what I'd gotten from a center of mass perspective.